In this video, I would like to do a sample calculation of a constant pressure calorimeter or a coffee cup calorimeter. So this is a simple experiment that can be done in most labs, which involves basically using water as the medium to do a chemical reaction, and therefore there is no change in pressure. So the pressure stays constant, so the reaction, such as an acid-base reaction, takes place in an insulated cup so that there's no loss of heat to the environment, and the reactants are quickly mixed in the cup, and the cup is sealed with a loose-fitting lid, and then the temperature is recorded as the solution is mixed and the reaction takes place. So there's no work done, so all we see developing is the heat of the reaction, and then we can translate that heat of the reaction to the enthalpy based on the moles of reactant that we added. So here we have one example of a typical experiment, such as the one that is often done in general chemistry labs. So we have a 50 milliliter sample of an acid and another 50 milliliter sample of a base, and usually you try to keep the concentrations the same so that or at least the number of moles that you add the same. So if you had a 50 ml sample of 0.250 molar solution and then maybe a 25 milliliter sample of a 0.5 molar solution, so the number of moles always stays the same. In this case, let's look at this example here. So we then have we can therefore figure the heat of the released by the calorimeter right here. So that is the heat from the calorimeter. That's basically gives us then the idea of how much heat the reaction has lost. The calorimeter will get warm. The water in the calorimeter will warm up slightly. So we see that right here. So we start with the solution at 19.5 degrees before mixing, and then we mix them together. The temperature rises to 21.2 degrees. So the delta T for this reaction right here is then 1.7 degrees. So we can write that out right here. The delta T is 1.7 degrees. And then we can calculate the heat of the calorimeter equals the mass times the specific heat times delta T. And now the amounts of solution right here are given in milliliters. And so because this is water, we can make the assumption in many cases that the density of water is 1.0 grams per milliliter. So we can therefore convert these 50 milliliters to grams, which is the same number if we do that conversion right here. So then we know then that each of those is 50 grams. So then the total mass of the solution is going to be then 100 grams times the specific heat, 4.18 joules per gram times degrees Celsius, times delta T, 1.7 degrees, and the units cancel out nicely. And we're left with 711 joules. And now this is the heat in the calorimeter, so this has a positive value. Now the heat for the reaction is going to be the negative of that value because the reaction is losing heat. So it is an exothermic reaction. So it's getting warm, we see right here. It is so if in doubt, always use the correct intuition that this reaction is heating up the solution. So therefore it is an exothermic reaction. So the heat of the reaction should be a negative number. Now we can express this now. So this would be perfectly fine as the enthalpy of the reaction if we had 1 mole of every substance. But we do not. We need to then figure out how to convert these solutions right here to molar amounts. So to do that, we just use the concentrations. So and express delta H in molar amounts. Delta H in kilojoules per mole, in kilojoules or joules per mole. And let's do that here in the next page. So we can then calculate, for example, the number of moles of HCl. And that is, so we have 0.05 liters times the molarity of the solution, 0.250 moles per liter. And we have left 0.0125 moles of HCl. And we see the same thing with NaOH. It's the same math right here. So the number of moles of NaOH is the same. 0.05 liters times 0.250 moles per liter equals 0.0125 moles of HCl, of NaOH, I'm sorry. And the same thing with the number of moles of water that are being produced. So we can express this with all the reactants right here. So remember the reaction that we're looking at right here is NaOH, aqueous, plus HCl. It makes H2O plus NaCl aqueous. That is our acid-base neutralization reaction. Acid and base makes water and salt. So we also make, and this is now balanced. So we always use then the number of moles in the reaction that we have available. So then this will also make, because we're starting with 0.125 moles of HCl, 0.125 moles of NaOH, so we end up with the number of moles of H2O produced. We can just do that. So we can start with either one of them. So you need to find out which is the limiting reactant in case you have a limiting reactant, but ideally you do not in these types of calculations. So the number of moles of H2O, we can just start off with, say, the number of moles of HCl, 0.0125 moles of HCl, and you'll get the same. And we know it's 1 mole of water for every 1 mole of HCl. And we're left with 0.0125 moles of water. Now we can then determine the delta H on a per molar amount. So then we have minus 711 joules that we calculated for the reaction as written, but we have 0.125 moles of all these reactants. So it would then be minus 711 joules divided by 0.0125 moles. And it is then going to be 56,880 joules per mole, or in kilojoules per mole, just divide this by 1,000. We end up with 56.9 kilojoules per mole. That's a more easily digestible answer. So that would be sort of the nice final answer. This would be 56.9 kilojoules per mole of water, NaOH, or H2O. If something like this would have a different molarity, then you would have to report it based on the reaction as written. So usually you just report it with the smallest coefficient, and then anyone who wishes to figure out which the delta H is for the reactant with a different coefficient, they can adjust it based on the stoichiometry of the reaction. So this would be it. And so this would be the reaction. One thing to notice right here is I forgot the negative sign. And so that is very important right here. Let's make sure we put that in. So this would still be negative because we're starting here with negative. And then this would be negative. Again, this is an exothermic reaction. So therefore, the delta H is negative. Thanks for watching.